Okay, so let's get started. Uh, Good morning, good afternoon, good evening, everyone, depending on the location. I'm Koji Yamashita, the moderator of this webinar from UC Riverside. Welcome to the IBPS Footage section webinar. Our footage section covers a wide geographical area stretching from West Covina to the eastern end of California and from Temecula to Baker. Today, we are honored to welcome our distinguished speaker, Dr. Julia Matevosyan from the Energy Systems Integration Group, also known as ESIG. Thank you for joining us. Before we begin the presentation, let me introduce our speaker. Dr. Julia Matevosyan is the ESIG's chief engineer and has more than 20 years of experience in the power industry. Prior to joining ESIG, Dr. Matevosyan was the lead planning engineer of the Electric Reliability Council of Texas, also known as ERCOT. This is one of the RTOs in the US. In her time with ERCOT, Dr. Matevosyan worked on the adequacy of system inertial response, system flexibility, frequency control, and performance issues related to high penetration of inverter-based resources and ancillary services market design. Dr. Matevosyan received her BSc from Riga Technical University in Latvia and her MSc and PhD from the Royal Institute of Technology in Sweden. If I remember correctly, she has been a proactive and representative SIGRE C2 and or C4 member who has often been invited as a speaker in many SIGRE events. So as you know, Dr. Julia Matevosyan is a rising star in the Power Engineering Society. Well, I will skip sharing my screen. So the Julia, fire away.
All right. Thank you so much, Koji. Thanks for having me and for such a nice introduction. And it's C4 in SIGRE. Let me share my screen. Koji, can you confirm you can see my screen well?
Yeah, now it's a presentation mode.
All right, sounds good. And I realized, good afternoon, well, good morning, good afternoon, everyone, depending where you are. That's right, people probably from everywhere. And before I go into my presentation, I realized I probably should have had a slide on ESIG and who we are. So maybe I'll just take a minute to talk about that before I proceed. So Energy Systems Integration Group, we're educational nonprofit organization, and we provide a forum and education for engineers in topics related to energy transition. And we do this through webinars and workshops, and we also operate, we are membership based, and so we also operate as a number of working groups, not very dissimilar to SIGRE, though our working groups take slightly shorter time, and so we try to kind of produce information that helps working engineers with their daily tasks. We have a lot of information that's public. All of our webinars are available to everybody to attend, and we also record everything. So if you are interested in ESIG, you can just look us up at esig.energy, and that's our webpage. So you'll find a lot of resources there. You can sign up for our future webinars, as well as just Google us for ESIG YouTube channel, and you'll find all recordings from previous webinars there as well. So a lot of topics related to electrical engineering and energy transition. All right, so that's enough about ESIG. And today I'll be talking about grid forming, inverter-based resources, emerging standards. I'll also talk about why grid forming a little bit, and also how grid forming inverter-based resources are incentivized in different countries. And when I say inverter-based resources, I mean wind, solar, storage, so generation resources that use inverters in the interface with the grid. So first of all, kind of why are we talking about grid forming today? Why do we need grid forming? Still majority of inverter-based resources today, so solar storage and wind resources, they're so-called grid following. So what they do, they kind of read voltage and frequency of the grid, lock onto that, and inject power aligned with that grid signal. And that grid signal comes from synchronous generators today. So that's how power system was designed historically around principles of synchronous generators. And the further wind and solar generation resources are from synchronous generators, the weaker is the grid. So you'll hear this term weak grid. And so what it means is that this part of the grid is far away from synchronous generation. And so the signal that inverter-based resources need to synchronize with the rest of the grid is easily perturbed by injection from this same inverter-based resources themselves. And it makes, in turn, hard for them to synchronize to the grid. And that may lead to local instability issues. So basically, the term grid following comes from the fact that inverter-based resources needs a strong signal from the grid, strong voltage signal from the grid to synchronize to the grid. But also, on the other hand, as inverter-based resources inject current into the grid, this signal is easily perturbed if they are far away from strong sources, strong voltage sources. So what happened over time, and just let me grab the pointer. This figure on the left-hand side is a schematic. It's not, it's not something to like that has physical meaning. It's more of a cartoon. And so what you see on the left-hand side is the strong grid condition, and maybe it's 0% of inverter-based resources on the grid, versus what you see on the right-hand side is weak grid conditions when you have just a few synchronous generators on the grid, or you are far away from them, and then you are almost at 100 or at 100% of inverter-based resources as a share of electricity demand at the time. And so what this is showing here is that anything above blue line is kind of stable condition, anything below blue line is unstable condition. Again, this is just a cartoon, doesn't have a physical meaning. And so initially when there are just a few inverter-based resources on a given grid, only kind of very few requirements were posted for inverter-based resources. So they were just not required to do anything. The main goal was to inject megawatts to the grid, and very little grid support was required from them. And as the shares of inverter-based resources were growing on the grid, then system operators started producing interconnection requirements. These are called grid codes in some other countries. And so on. So they were trying to stipulate inverter-based resources to help the grid. And this is when we get this, you can hear low voltage write-through, high voltage write-through requirements, and some other grid-friendly features. As we progress towards maybe 30-40% penetration of inverter-based resources, even more requirements are being put on inverter-based resources themselves. So there is so-called weak grid features, so where inverter-based resources are required to behave more stably in weak grid conditions. Control interaction mitigations, maybe some of the additional devices are being added on the grid to maintain stability. As we move towards even higher shares of inverter-based resources, maybe like 70% or 75%, then even further control advancements are needed from grid following inverter-based resources, but also now system operators start looking at synchronous condensers. So synchronous condenser is a synchronous machine without a prime mover. So it has some of the capabilities of a synchronous generator without injecting megawatts into the grid. And so system operators go for these support measures to maintain grid stable as penetrations of grid following inverter-based resources are growing. And as we start to progress, maybe I would say last 20%, it depends on the grid, but around like last 20% of penetration from inverter-based resources, then this is where we start to look at even further control advancements from inverter-based resources, and this is where grid forming. So this is a new type of control for grid-connected inverter-based resources where they behave more like a strong voltage source in somewhat similar manner to synchronous generators. And having some percentage of this type of resources on the grid would allow to get to 100% inverter-based penetration. So theoretically, and also there are like island grids where you can get to 100% penetration with just inverter-based resources, and you don't need synchronous machines, potentially. All right, so what are the issues? I kind of touched on that in the previous slide. But as synchronous generators are going away and being displaced by inverter-based resources like solar storage, wind, synchronous machines are becoming scarce, and we need to lean more and more on inverter-based resources for provision of services. The issues that grid can encounter are related to frequency stability. So this is related to low inertia, leading to fast rate of change of frequency after generation contingencies or load contingencies. So large generator trips and the frequency decline is too fast, where you cannot arrest frequency in time, and it may lead to under frequency load shedding or just instabilities on the grid. Too fast frequency control that grid following inverter-based resources can provide very well, but it may introduce oscillations, especially in low inertia systems. And then there may be common mode events that could potentially result in multiple inverter-based resources tripping simultaneously. And this may lead again to frequency events that have not been seen before, where you had fewer synchronous machines and they had no common mode tripping behavior, maybe. Then there can be voltage and angular stability issues. So one of the things is that renewable resources are usually far away from, large load centers, large cities. And so what happens there is that you end up having long distance high power transfer, so having to transfer large amounts of power from generation pockets where renewables are rich to load centers. And this may cause steady state voltage instability problems. Then for those previously, there was kind of like very clear signal that the system is leaning towards being voltage unstable and that you are at the kind of getting close to voltage stability margin. Whereas now it may look like it's normal voltage conditions, operating conditions, and then very small change on the grid may lead to voltage collapse. And so that the term that sometimes is being used is like system becoming more brittle. So it's like it takes a longer time maybe to get to instability, but like once it happens, it's very abrupt and hard to contain. And then in areas with low system strengths, you can encounter voltage oscillations. And then control stability. So these are all inverter-based resources. They're all control-based, and there may be interactions between different controls of different resources, and maybe they like fighting each other. And those are more prominent in weak grid conditions. And so all of these issues, I also mentioned it in the beginning that, all of these issues will not happen at the same time in all of the systems. It actually depends on type of the system that you are in. And so in small electrical islands, for example, like Hawaii, they will experience a number of issues all at once. So like all of these issues that I mentioned previously. But on the other hand, the grids themselves on the smaller islands, they tend to be more meshed, and overall coordination of solutions is easier than in large large grid, like say, for example, Eastern Interconnection in the US. Then there are medium electrical islands, like for example, Ireland, and again, systems there are more meshed. Frequency usually becomes an issue first before weak grid or voltage challenges. Larger electrical islands like Great Britain or ERCOT, so Texas system, mainland Australia, the first challenge that you encounter with integration of inverter-based resources is this weak grid conditions, where you have pockets of the grid that are high on renewables, and those are far away from load centers where synchronous generators or strong voltage sources are. And only then inertia becomes or may become an issue. And then in geographically large interconnected systems like Central Europe, Eastern interconnection, Western interconnection, in the US, there may be no issues with inverter-based resources for a long time, because to reach this high percents of inverter-based resource penetration, it will take much longer. But then the concern there becomes, first of all, having these weak grid pockets, again, having voltage issues there, control interactions issues there because of weak grid conditions. And then the other concern in some of the grids that operate in like where system splits are possible, then keeping those islands stable once the system splits, then that becomes a problem. Because some of these islands will end up with more renewables and other islands will end up with more synchronous generation. So for example, Texas grid, they don't operate this way, they don't split. So if they, if there is a blackout, the entire system goes down. Whereas in Central Europe, I believe it splits in 3. And so then it becomes an issue that each of the islands may not be able to operate stably after the split. So just with an example of ERCOT system, I just wanted to illustrate all of what I talked about before. So this is just a Texas system, and ERCOT is a system operator in the majority of state of Texas, 90%. And you can see areas that ERCOT covers. These are all colored areas. The ones without color, ERCOT doesn't serve. So anyway, primarily wind and solar resources are concentrated here and here in the west part of the grid. And traditionally, these parts of the grids, they don't have much load. So they're far away from load centers. And most of the synchronous generation is here on the east side. So you can see here that, we are far away from load centers and far away from synchronous generation. And so what it causes, like weak grid conditions in Texas Panhandle, near Panhandle, and even like in West Texas, there are some voltage stability limitations and also risk of control interactions. What that resulted in is that over time, ERCOT started implementing what they call generic transmission constraints. So these are constraints that have, due to stability risks. And so these constraints are defined based on offline studies and then maintained in real time, so or respected in real time, so that dispatch that the market engine comes up with doesn't violate these constraints. And you can see that over time, the amount of these constraints is growing. And this is concerning because it in turn causes curtailment of renewables. So you have kind of cheaper and clean sources of power, this in the west part of the grid, but because of transmission constraints, you cannot transfer it to load centers, and the renewables are curtailed this way. Here you can also see peak load in ERCOT is 85.5 gigawatt. Instantaneous wind and solar penetration that they have achieved so far is 75%. So this is like, if you remember the first slide that I was showing, you'll recall that we are kind of at this stage where you need some additional measures on the grid to maintain this high share of grid following inverter-based resources. Inverter-based resources already have some stringent requirements applied to them, write-through requirements, primary frequency support requirements, voltage support requirements. They're still all grid following, so there is no grid forming requirements yet, though ERCOT is working on it. and still with that, there needs to be some additional measures to maintain stability. And if you compare peak load and with installed capacity of wind and solar, you can see that these numbers are very high. So it's almost 40 gigawatt of wind, almost 30 gigawatt of solar, and almost 10 gigawatt of battery in ERCOT. This chart here on the right-hand side is showing how curtailments are overall kind of the trend is towards growing curtailments in ERCOT. The bars are showing installed capacity, blue is wind, yellow is solar, and then the blue line is showing wind curtailment in percentage of annual production, and red is solar curtailment. And so overall curtailment is growing because of this growing number of stability constraints and growing installed capacity of wind and solar in these areas that are constrained. So what can be done to relieve the stability constraints? First of all, I just will talk about what can be done kind of traditionally and based from a grid perspective as a system operator. ERCOT is looking to put in synchronous condensers. As I mentioned, these are synchronous machines without prime mover, so they are providing voltage support and reactive support, voltage support. They can provide additional short circuit current if that's needed. If a flywheel is added to synchronous condenser, it can also provide more inertia overall because prime mover is not there. Synchronous condensers inertia contribution is relatively small. So ERCOT already installed two synchronous condensers previously, maybe 2016, 2018 timeframe, if I remember correctly. But now they are looking to put in 6 more synchronous condensers, and this is in this kind of Panhandle, West Texas area to support weak grid, to kind of improve weak grid conditions there. Additionally, what can be done, more transmission can be built, and this is not because there is a need for transfer capability, but to remove this weak grid situation again. So weak grid situation basically means that impedance between the generation source and load is high. And so by putting parallel transmission lines, the idea is to reduce this impedance and basically it electrically brings inverter-based resources in West Texas and Panhandle closer to strong resources in the east. And so more transmission have been built between West Texas and the rest of the grid in ERCOT. But these measures are kind of generic. I'm just using ERCOT as an example, but these are used around the world to improve system strength conditions. But then the question becomes, can something be done with inverter-based resources? Because it seems like, you know, all of these measures are necessary with addition of inverter-based resources. And so can these resources themselves do something to relieve stability constraint? And so this is where grid forming comes in as one of the solutions. I just put here a definition of grid forming that a NERC white paper has defined, and I have a link to the white paper here at the bottom. And I'll just read through it because there is no other way around it for a definition. So grid forming inverter-based controls, the idea here is that they maintain internal voltage phasor constant or nearly constant in subtransient and transient timeframes. So they basically act as a strong voltage source. And what it does is it allows inverter-based resource to immediately respond to changes in external system and maintain inverter-based resource control stability during challenging network conditions. The voltage phasor must be controlled to maintain synchronism with other devices on the grid and must also regulate active and reactive power appropriately to support the grid. There are many variations of grid forming controls, similarly to grid following controls. There are also many variations there. Both types of controls are subject to physical equipment constraints, including voltage, current energy limits, mechanical equipment constraints if we're looking at implementing grid farming in wind turbines. They can also be external power system limits. So it's, grid forming is not a silver bullet and will not make all of the issues go away. Usually when grid forming requirements are developed by system operators, the idea is that those are in addition to requirements that already apply to grid following resources. So basically, if you implement grid forming controls in inverter-based resource within equipment limit, it will be able to provide most of the services that are currently provided by synchronous machines. And so by synchronous machines provide the services maybe by design, because this is how historically power systems have been designed. But now inverter-based resources with grid forming controls can do all of these functionalities too within equipment limits. The grid forming inverter-based resources have stabilizing effect in weak grid areas, and they can improve stability for conventional grid following controls or inverter-based resources. And so basically, if you think about it, if we could implement grid forming controls on inverter-based resources that are going onto the grid in the next few years, they can provide cost-effective alternative to, example, synchronous condensers or new transmission lines to improve stability. But in this case, the improvement is coming from the new inverter-based resources themselves, as they are being added to the grid. And so you are avoiding need for additional transmission assets to improve stability. So this is just illustrated here with a little example. It's I mean, here again, a cartoon, but I have a report linked up here, and we have a little test study there that is showing in the simulation that this is how it works. So you have, it may be a grid similar to Texas Panhandle. It's far away from external grid, far away from strong grid voltage sources, and you have grid following inverter-based resources on this grid. And so now you are maybe planning to add another grid following resource, maybe a battery, to the grid. And so what happens there in the study, it shows that if this part is disconnected from external grid, or maybe like large disturbance is happening on external grid, this part is becoming unstable because it's weak grid conditions and there is no synchronous generator in this part of the grid. So what needs to be done then, synchronous condenser needs to be added to improve stability. And if we add a synchronous condenser, then there are no issues and the grid can operate stably after contingency. But this is additional cost, right? You need to have new transmission asset built, and this causes additional cost. But if, on the other hand, this new resource that will be added anyway, if it's added with grid forming controls instead of grid following, then even for contingency conditions, this part of the grid can operate stably and you don't need a synchronous condenser here. So you can basically avoid additional transmission reinforcement by changing controls on the resource itself. And this, of course, will be saving costs because you are avoiding this new transmission assets. So potential use cases for grid forming controls, you have weak grid operation that is, becomes possible. It can damp voltage and frequency oscillations, resist voltage phase angle changes, resist frequency changes on the grid, kind of in a similar manner as synchronous generators do today. Provide fast fault current injection, balanced and unbalanced, mitigate subsynchronous control interactions, support islanded operations where required. As I was saying, not everybody operates this way. Provide black star capability when required. So these two latter applications, they require a bit more careful design considerations and may require additional hardware in inverter-based resource to provide this support, because it requires a bit more support than this other potential applications. So seeing kind of this benefit from grid forming controls, system operators and research organizations, regulators around the world started producing grid forming testing and interconnection specifications. So this is what you can see here kind of at glance. I will focus primarily on system operators, but you can, look at others maybe at your time. Here I have a link. If you go follow this link, it will take you to a webpage at ESIG webpage where we keep track of all of these documents. And the links to all of these documents are provided on that page. So Hawaii, they started first, and at some point in 2019, they decided that all future energy storage that will be built on Hawaii Islands will be grid forming. And so this first specification defines it for this grid forming batteries. The national grid in Great Britain, they were the first large system operator that came out with grid code for grid forming. Initially, it was a voluntary grid code, but I'll talk about incentive in a minute. And then in 2023, again, National Grid, they released a document that is kind of like an application guide. So it basically explains how do you test and how do you prove that indeed an inverter-based resource is grid forming. And so most of the tests are simulation-based, but still it kind of explains how you do it. And then IEMO, system operator in Australia, released their requirement for grid forming as a voluntary requirement again. And then they followed next year with testing specifications. FinGrid is an interesting one. They initially put in specifications for grid forming batteries into a special study document. So basically for the batteries that go into weak grid areas, they can require special studies that are normally not applied for inverter-based resources. And so as a part of the special studies, then batteries tested for grid forming capabilities. And so this introduces a requirement for all batteries that are going into weak grid areas to be grid forming, but they currently actually working on the draft for the grid code, draft is already out there to require all future batteries to be grid forming. And then NERC white paper, I mentioned already, it kind of provides recommendations for how to specify grid forming and what to require from grid forming, as well as kind of incentivizes grid forming in battery storage. And then currently MISO also has requirements for grid forming batteries. It's almost kind of through with the stakeholder process, and you can consider it as being approved. And ERCOT currently in the stakeholder process, they also have documents that are requirements for all future batteries to be grid forming. ENTSO-E is Association of System Operators in Europe. So they have since 2019, as an effective date, they have requirements for all inverter-based resource or for all generation resources in Europe that are part of ENTSO-E. And the requirements are harmonized across ENTSO-E member states. So now they have an update in works that will require future resources, inverter-based resources, to be grid forming as well. But this have not been approved yet and currently with European Commission for consideration. And then the most recent one that I've seen, I haven't had a chance to read through it yet, is Chilean system operator put out requirements both for grid following and grid forming, for grid following resources and grid forming batteries. So the draft is out there for stakeholder review. So here is the same kind of list of system operators and research organizations, but you can see it kind of split into which documents are produced by system operators, which are by research organizations, which are published, which are still drafts. And there are some planned ones that I just have heard about, but there are no drafts out yet. Requirements vary pretty widely between these documents, from high level to slightly more detailed. Some are just functional specifications, others are specifications and tests. And there are also specifications that are just a set of tests. There are no like real detailed requirements, but more just how you in a test prove that you're indeed grid forming. Requirements may be split into core requirements and advanced capability requirements. Some are voluntary, some are mandatory, and I'll talk about this in a minute. And then, as I mentioned, all of these are in addition to grid following requirements, unless there are conflicts. And then if there are conflicts, then it's clarified. And then some requirements apply to all types of inverter-based resources, like, for example, ENTSO-E requirement, if approved, will apply to all, whereas others apply just to battery energy storage. And I've done a webinar where I went more in details into each of the requirements. And so if you're interested, you can click, there is a recording and slides are available at ESIG webpage. And so you may ask why grid forming in the battery and why not all inverter-based resources. Potentially, you can implement grid forming in any type of inverter-based resource, but grid forming behavior requires certain amount of energy buffer, which in wind and solar will mean that they have to operate below what's available in wind or solar irradiance, and they will lose. They will have to lose revenue by operating this way. In addition, grid forming controls in wind turbines require more design considerations because they result in greater mechanical stress. So it needs to be considered from the design stage of a wind turbine. Whereas in battery, there is already energy buffer available, and so only software modifications will be needed to operate in grid forming control mode. And so therefore, batteries have seen as a lower hanging fruit for grid forming implementation. Keeping in mind is you can think, okay, so if it's so easy to convert to grid forming, why don't we continue building them as grid following and then convert it later? But retrofitting is always difficult because they can be contractual agreements that pose limitations. You will need additional costs for restudies, and you will need to take them out of operation, during which time they'll lose revenue when changing, these controls. There is a number of grid forming batteries already built around the world. The last slide in my presentation actually has a list of products. I like this chart as kind of further explains why grid forming is easier in the battery and more difficult in solar and more difficult in wind. So basically, implementing grid forming in wind is like teaching a bear to ride a bicycle, whereas implementing grid forming in a battery is like teaching a kid to ride a bicycle. So it's much more straightforward. Energy storage is already there. It's all just software changes. So it's just the implementation itself is easier. This chart on the right-hand side is from Lawrence Berkeley National Lab. They track interconnection queues in the US, and you can see by technology how much battery capacity is coming to US grids. And so this is why there is kind of this, not only it's a lower hanging fruit to implement grid forming, but there is also the short window of opportunity where all of this capacity that is coming from storage and is planned in the next few years can potentially be built as grid forming and can provide stability support to the grid and support grid following wind and solar that is coming. Here, just between those documents that I've shown, it's showing a split where requirements only apply to batteries versus where requirements apply to all types of inverter-based resources. So as I mentioned, Hawaii, MISO, ERCOT, NERC, FinGrid, Chile, they all focus on grid forming batteries, whereas National Grid, it doesn't call out batteries necessarily, but they also specify that specifications basically call for energy buffer. So still, even if it's a grid forming wind resource, you will still need some kind of energy storage on site. ENTSO-E is also technology neutral. IMO is technology neutral, but again specifies the need for energy buffer to provide grid forming functions. And there is this VDE FNN requirement that is also kind of technology neutral, doesn't call battery out. This just showing grid forming progress globally in terms of specifications, again, focusing just on system operators. And on the right-hand side lists manufacturers that I've heard of, like in different projects that already have grid forming capability offerings. And you can find more details on this on ESIC webpage as well. So if you look at grid forming specifications, we're not planning to go in detail for all of them. As I said, there is a lot of variance in details, but specifications themselves are at high level relatively similar. So the functions that people are looking for in grid forming are similar. And this is responses to voltage phase angle step, response to voltage magnitude step, limiting rate of change of frequency after generation trip contingencies or load trip contingencies, active power sharing amongst all grid forming resources, including synchronous machines, behavior at current limit. Sometimes it is described explicitly, sometimes it's implicit within these other requirements, but people talk about how grid forming is expected to behave at current limit. Requirement to counter imbalances and counter harmonics, provide damping, not cause additional control interactions, and be an interoperable, low system strength operation, islanded operation, and then ability to resynchronize back to grid connected operation, surviving loss of last synchronous machine. So this is a test and a simulation. In majority of the requirements, it's not an expectation that grid forming resource is supposed to support the grid without any synchronous machines, but the test is used kind of to prove grid forming capability ultimately that it's there. And then black start capability, I kind of colored it differently because it's not everywhere, and everywhere where it is mentioned, it is defined as advanced capability that will require design consideration. So it's like a special requirement, usually paid for. So next, I just wanted to talk a little bit about incentives versus requirements. So in some of this, as I mentioned, some of the specifications are just voluntary. Others are like strict requirements for specifically for battery storage to be grid forming. So voluntary, as I mentioned, Great Britain National Energy System Operator came out with voluntary requirements first, but then gradually they switched to incentivized capability, and I'll talk about how they incentivize it. And now they are working on towards like maybe making it a requirement, following into ENTSO-E's footsteps. In Australia, it was first released as voluntary requirement, and this is where it is right now. In Germany, there is currently kind of market product that they're considering, but they also realizing that if ENTSO-E requirement will go in force, it will apply to Germany as well. And so the idea is that after a few years, it will be a requirement. And then all of these countries, system operators, they require future batteries to be grid forming. So now just jumping in a little bit more in details of what it means, incentives versus requirements. So in HECO, in recent studies in Hawaii, a system operator there in recent studies found that grid forming batteries is the most effective resource to support grid stability. And so they came out with requirement for all future batteries to be grid forming. And then as they go forward and they procure resources through competitive RFPs, they have megawatt hour targets and sometimes megawatt targets for grid forming batteries. So they procure a certain amount of batteries and those are grid forming. And then alongside, they also procure firm capacity as wind with battery storage and solar with battery storage. In Great Britain, as I mentioned, initially requirement came out as voluntary, but then they ran a number of tenders looking for stability services from any type of resource that can provide. And they call them Stability Pathfinder. So the second phase of Stability Pathfinder was open for new technologies, including grid forming batteries. And so alongside synchronous condensers, 5 grid forming batteries were awarded. And then National Grid followed with development of stability market design and developed eligibility rules and how they're going to procure, and midterm stability market launched in 2023. But as I mentioned, in September this year, National Grid started looking at potentially requiring grid forming capability from the largest type of generating modules, so 50 megawatt and up, connected at 110 kV and up, for all of them to be grid forming. And also that also includes HVDC systems, including interconnectors. And so if this requirements goes into force, the compliance will be required from 2028, but it will not be retroactive to the existing resources. IEMO requirement is interesting. So as I mentioned, the specifications they released were voluntary initially, but they have this requirement for transmission owner to maintain minimum system strengths in certain areas of the grid. And as grid following inverter-based resources are going into these parts of the grid, they are assessed for the impact on system strengths. And if they are determined to deteriorate system strengths, then they need to pay to the transmission owner to bring the system strengths back to this minimum level that transmission owner has determined. Or potentially they can bring their own grid forming resource or some kind of system strength support and not pay to transmission owner. So that incentivized co-location of grid forming batteries with planned grid following inverter-based resources. So it's not quite a market, but there is this type of incentive that led to more development of grid forming batteries. And additionally, Australian Renewable Energy Agency provided some support to 8 new grid forming batteries that are currently under construction. And the idea was to just support this new technology deployment. As I mentioned, MISO, they have presented their latest drafts of proposed requirements for all future batteries to be grid forming. The proposal is to require capabilities from all batteries that will go into the next generation study cycle, so starting from beginning of next year. And the applications that will be studied, if it's a battery storage, then they will be studied for grid forming requirements. And this requirement is basically going into MISO's business practices manual starting from January next year. FinGrid, as I said, currently allows only grid forming batteries to build in big grid areas. So they basically can reject interconnection of grid following inverter-based resources in big grid areas. And ERCOT was looking at similar idea in the dynamic stability assessment in 2018, but currently they also went with a requirement for all future batteries to be grid forming. And this is something that they are currently working on. FinGrid, again, is looking to update the grid code to require all future batteries to be grid forming. ENTSO-E will require all future type B and D 2D power park modules to be grid forming. I have a table on the next slide to show what this means. And then in Germany, they are currently looking at developing this inertia market that will pay all new inertia providers for the next coming years. So this is just for your reference, showing in ENTSO-E requirements what is type B, type C, and type D generators. So it differs by country and voltage level. It's just for your reference to look afterwards. Oh yeah, sorry, I missed one slide here. One thing I wanted to mention on German market. So in Germany, initially they started with recognizing they have weak grid conditions already on the grid and looking at transmission assets such as synchronous condensers or building new transmission lines to improve system strengths in those areas. And then if and once ENTSO-E grid code, this one, ENTSO-E RFG 2.0 is approved, then all future resources of these types, this larger future resources, they'll be required to be grid forming. So they realize that in Germany, but there will be time between these two where they are looking to incentivize deployment of grid forming technology. And so they are looking to incentivize it through this new inertia payment. So that's kind of what I wanted to mention. And so last slide before I conclude, and maybe we can have some questions here. On ESIG webpage, I keep track of all grid forming transmission and sub-transmission connected grid forming projects around the world, because right now there are not too many yet. And I feel like in a few years, I probably wouldn't be able to keep track of them anymore. But here, if you click on this link and on this table here, you can see existing projects that are already in operation and ones that are under construction. So these are not speculative projects. These are already like broken ground and under construction projects. Primarily all of them batteries. There are a few grid forming STATCOMs and a few back-to-back HVDC stations. So I think I will not go through conclusions, rather leave time for questions, but basically grid forming is coming, requirements are being worked on. People do realize that grid forming and battery is more straightforward, and so this is where the focus is right now. Thank you so much.
Thank you for the very informative presentation, Julia. If you have audiences, if you have questions, please type using the chat window. And in the meantime, I have just one quick question about the battery types. You know, you might know that there are a wide variety of battery types, like lithium batteries, lead acid batteries, sodium sulfur batteries. And then, do we have the same requirements for the batteries regardless of the battery types? Now, why I'm asking here is that so we use, you know, the fault right-through requirement can differ depending on the battery type in Japan. So because there are some like a chemical, you know, how to say, the reaction time. So we have like a different, for example, the active power recovery period or the different fault durations are required depending on the battery types. So if we switch from grid forming converter to grid forming converter, can we apply the same requirements for the battery grid forming converters regardless of the battery types?
Yeah, so it's very interesting. I actually didn't know that that's what's happening in Japan. Overall, I would say the tendency of system operators is to define in as technology neutral manner as possible, looking more at what's needed on the grid side. So this is how the requirements overall are formulated initially. And then maybe they realize there are some technology differences. So sometimes you can see slightly different requirements applied to wind compared to solar and storage inverter-based resources. I'm just talking about generally requirements, not grid forming specifically. And then, yeah, some solar, like recognizing that there is no sun at night, and so they will not be able to provide everything at zero output. But yeah, on the battery side, I haven't seen differentiation. It's more of like what system operator wants, but also realizing, I would say like it's more just with inverters in mind without thinking of a prime mover too much.
I see. That's interesting because in the case of like a fuel cell batteries, and we can allow more time to recover its output. And then also we can shorten the fault duration in the case of fuel cell batteries in Japan. But anyway, yeah. And I think
it's an interesting question. I'll look it up.
Yeah,
I didn't know
can
that.
you quickly open the chat window? There is one question from one of the audiences.
I'll open the chat window. That's a big question. As regards to accounts batteries, when it comes to utilizing batteries. This one was also about chemistry, not technical matter. Yeah, I would say politicals. I'm not sure if having long-term storage would matter all that much. I feel like the focus for grid forming specifications is on very short time frames, like in milliseconds, maybe to a few seconds. And so people are not looking to have like longer duration storage for grid forming, maybe for like black start application or islanding and then resynchronizing back type of application. This is where duration will be more important. But for like on the grid operation, for grid forming, it's all, even like ultra capacitors. So grid forming STATCOM with ultra capacitors would be sufficient. So several seconds of energy storage is enough to like arrest, and then grid following resources and maybe like remaining synchronous generators can provide the rest as a like frequency control and voltage support, which is slower.
Yeah, Julie, we have one more question from Stanko on the bottom.
Yeah, I'm not sure about readiness of the distribution grids to support grid forming, because there is more considerations like in terms of protection, and with the fact that the distribution grid's primarily designed for the power flow to go, the other way. And another one is like if you have, say, islanding in a distribution grid and you have a strong source there, there may be some safety considerations that need to be taken into account. So I would say like it requires like case by case considerations. I'm not as familiar with distribution grids. I know there is like of the projects that I have on the in the table, one there is a 25 kV network, so it's at the end of the very long 25 kV feeder in Cape Cod. That's about as much as I know. I know there are people like doing research and looking at grid forming in distribution grids as well. Control criteria for grid forming sources. Understood. Now yeah, so it's, I mean, the question is about if under certain grid conditions, grid forming may become unstable. These are kind of what I was focusing on, are interconnection requirements. But as with grid following resources, grid forming resources, as they get on the grid, there needs to be studies, like all of the interconnection studies that currently apply to grid following resources will be applied to grid forming. And so potentially system operators or utilities will be able to catch any conditions that may become unstable. It can be mitigated by tuning control parameters. Overall, in ESIG, we have a task force that focuses on benefits of grid forming, and they have done a study, like project team there have done a study. They were basically able to achieve stability with pretty much off-the-shelf grid forming models from available manufacturers that have capabilities. But they still are also saying that this conclusion shouldn't be generalized, and it needs to be studied on case-by-case basis. One other thing I heard that in stronger grids, that there may be more potential for grid forming controls to become unstable, so more attention needs to be paid to strong grid conditions rather than to weak grid conditions, so it seems. For magnetic, I'm not sure about this question about magnetic isolation, right? I'm not familiar with that. So sorry, will not be able to answer that question.
Yeah, no worries. But if we how to say require the grid forming converters for like a residential PVs in the future, for example, in this case, do you think some like a potential conflicts between the like anti-islanding protection and then also the the GFM's like a capability to maintain the grid?
Yes, yeah, I think that's what will need to be rethought. Because the distribution grids were not designed to have sources that support an island, right? The entire philosophy of detecting an island is based on the fact that now you have a grid without voltage sources. Yeah,
I see.
That will require some rethinking there. Yeah.
Yeah, I started
even now with the even with grid following resources. So what happened in Ireland and in Great Britain a few years ago is where now with so the both of them used to use like rate of change of frequency protection to like detect, like anti-islanding protection was based on rate of change of frequency. So if rate of change of frequency is high, it assumes it's in an island and then disconnects. But with proliferation of inverter-based resources and inertia going down, now this rate of change of frequency became kind of normal thing for generator trip, and it's not an island detection thing anymore. So they had to change settings on the protection to be less sensitive to rate of change of frequency.
I see. Although I have lots of questions, but I'm sorry, but the time is up. So I think we have to close the webinar. So everyone, our next webinar is planned to be held sometime in January next year. And the speaker and the date of the webinar are not determined yet. And once they are ready, and then the flyer will be uploaded to IEEE tools. So please stay tuned. And also, Julia and everyone, happy Merry Christmas and a prosperous 2025. Thank you, everyone.
Merry Christmas, and thanks for having me.
Thank you, Merry
Thank you for
Christmas.
joining us.